The final lecture for the series or the semester is going to be on angular kinetics. And so this will be your final module. You wrap up your module 3 and show you the angular analogs of Newton's laws as well as the lever systems. So defining angular kinetics, we talk about the cause of angular motion. Again, remember the kinetics part of things is the cause of, where the kinematics is the outcome. It is very similar to the linear component or counterpart, except for this component of distance. So the meters here is the distance at which the force is applied. And the angular component or analog of force is torque, because it includes that distance measure. It's going to be very important that you understand that we talk about the perpendicular distance. You'll also see it written as d subscript perpendicular line. But the torque is a combination of the force and the shortest perpendicular distance to the axis of rotation that the force is applied. We'll talk about how to do that. But again, so we're talking about the moment of force. So the force times that perpendicular distance is the moment of force application, and that's what torque is considered. So going forward, if you look at it here, the direction of motion, both are pushing in the direction of motion. But if I look at this as my axis of rotation here on the left, and I push this way, there is a rotational component. So that push of the right hand causes a rotation about the left, which is if I had the brake on. And then we can talk about how to calculate the torque. But here it looks like in a little more schematic. If the force is applied to the axis of rotation, you'll have some sort of translation, and that's where there's just a force is a linear component. Again, if I have a force that's applied in a perpendicular distance, so it's completely perpendicular or 90 degrees from the axis of rotation, there's my moment arm, because it's the shortest perpendicular distance from the axis of rotation. However, if the force is applied at an angle to the axis of rotation, to calculate the distance or the perpendicular distance of the moment arm, here we have the moment arm, we extend this line out and we find the right angle of that force application. And then this distance here is your R perpendicular. It's your distance of the force applied in the shortest perpendicular distance to the axis of rotation. So this is where that perpendicular distance R or D perpendicular comes into play. If it's at an angle, then we need to calculate how much of that angle is producing rotation about the axis of rotation. And to do that, we have to extend it out for 90 degrees to find that perpendicular portion. So going into Newton's analogs, we're going to start with the law of inertia, and understanding that a rotating body will continue in that state until an external torque. And here you have the angular portion. So instead of force, it's torque. Here you have the same component, so there's no change in angular velocity. The torque, sum of the torques equals 0. Moment inertia is the quality of resistance to any change in motion. So just like inertia and the linear component, a moment of inertia is the quantity of resistance to any change in angular motion. And it's a component of the mass and distribution of the masses independently. So here we have moment of inertia. It's a sum of the masses times the radius at which those masses are squared. And so the distance the masses are from the axis of rotation goes into play here. Taking the law of inertia a little bit further, we're going to talk about the radius of gyration. And what your radius of gyration is, it deals with this rho here. And it's an understanding that the center of mass, or the particles, the sum of the particles of the system relative to the axis of rotation, must be in a location that does not change the rotational component. So it's a concentration without changing the inertial characteristics of the segment. So we'll talk about how people can manipulate the radius of gyration throughout this process. These are two great examples of how we manipulate the radius of gyration to create a reduced resistance to angular motion, and allows us to create a greater velocity or a greater spin through the process. Here you have the moment of inertia of the leg during different stance phases or gait cycle phases of the run. Moving on to Newton's second law, and that is going to be the law of acceleration. The angular analog is just the law of angular acceleration. So it's an external torque will produce or tend to produce an angular acceleration of the system proportional to the direction of the torque. And so here you have torque and its moment of inertia and angular acceleration. So F equals ma in the angular form. So the sum of torques equals the moment of inertia times angular acceleration. Taking the law of acceleration a little further, we talk about the angular momentum. Moment of inertia times angular velocity. Torque is the rate change of angular momentum. And so we're going to do the same thing we did with the linear component, and we're going to break this down into components of angular momentum and what Newton completely talked about. So here, if we break angular acceleration down, we have the change in angular velocity over the change in angular time, or not angular time, but the change in time. A little further, if we rearrange this, we have angular impulse equals angular momentum. So torque over a period of time produces how the moment of inertia and angular velocity change in the component. And here we have a little bit further. So the angular momentum and the torque. So angular momentum is I delta angular velocity. If we look at the torque, it's the change in angular momentum over the change in time. Just to go a little further, this is going to talk about the change in gait cycles. So if you look at the different segments of the body, you have arms, head, trunk, body, and legs, and how those are manipulated through a gait cycle in relation to each other. You can see the head and the trunk really don't change much of their angular momentum throughout the process, but there's a great change in the leg and the arms throughout the process. And the leg goes through a huge angular momentum change during these two phases of the process. The final angular analog for Newton's laws, or the third, it's the action-reaction, and that's for every torque. And again, so you can kind of see the pattern where we just take torque and substitute it for force. By one system, there's an equal and opposite torque on the system. And simply written, it's the same way we have if we had this sum of forces. It's sum of torques A on B equals a negative sum of torques B on A. So remember that the difference between torque and force is simply the addition of that perpendicular distance of the application of force relative to the axis of rotation. And that is where we get the torque. So the location of the center of mass, and this is something that we've talked about a little bit in class, and I chose not to do this in lab because it's just a simple calculation component. But the location of the system is at which the sum of torques is equal to 0. So that is the sum of torques equals 0 is the center of mass. So if I hang something from the ceiling, you're going to attach it to where your estimated center of mass is, and that causes it not to rotate. But here's an example. So say we had a long board, and we had two different masses, a 2 kilogram and a 3 kilogram mass. You can calculate the distance that each of these needs to be to create a balanced torque. Remember, here's the torque each of them creates in order to be balanced based off this process. So you can identify whether if a person A is 85 kilograms and person B is 100 kilograms, and the person that's 100 kilograms is 1 meter from the axis, you can calculate the distance person A would have to be in order to balance the board. And that's by making the sum of the torques equal. So you could be sum of torque equals sum of torque, and you know how to calculate each of these and to create a balanced equation. Each one of these is an example of how we use the center of mass in equating a sum of torques to balance systems in the environment, from both objects to an individual person in combination with objects. So each one of these is being able to balance the torque to create a balanced situation. The final component of this lecture in the class that we're really going to cover is lever systems. And the overall concept with lever systems is this mechanical advantage, which represents how the system is using the mechanics in relationship of force, axis of rotation, and resistance to produce what the desired outcome of movement is. So mechanical advantage is simply the effort arm divided by the resistance arm. And so the resistance is here, the resistance force, and the effort arm is over here on the other side. So we'll talk a little bit more about that. When we talk about lever systems, there's three possible advantages of the mechanical advantage. And it's simply a combination of the ratio of the effort arm to the resistive arm. Right? So whatever this relationship is, it has three possibilities. Those are where the mechanical advantage equals 1, where these are equal to each other. Less than 1, where the resistive arm is greater than the effort arm. Or mechanical advantage greater 1, where the effort arm is greater than the resistive arm. Okay, so the possibilities all represented are here. So the mechanical advantage of 1 is to alter the direction and motion balance of the lever. And so this is very essential, is it doesn't magnify either the effort arm or resistance arm. Whereas the mechanical advantage of less than 1 increases the required force to overcome the resistance. So this one again, so keep in mind, these are the important part, is the velocity or speed of movement is magnified due to the greater distance of the resistive force has to move through. Where the mechanical advantage of greater than 1 magnifies the torque created by the effort arm. Therefore, the effort force. Going further, I want to describe the three different classes of levers to you. So there's a first, second, and third class. We're going to start, of course, with the first class, and that is the effort force or the applied force is opposite the fulcrum or the axis than the resistive force. So this is an example of these are seesaws, balance scales, crowbars. Your mechanical advantage here can be 1. It can be less than 1 or greater than 1. So these allow for all of the different mechanical advantages to occur. But here's your resistive force, the applied force, and then your fulcrum. And when we're going to go forward and we talk about inside of the body, the effort force is going to be your skeletal muscle contraction force, and where the tendon or the insertion on the bone is in relationship to the resistive force and the fulcrum. So in the human body, we see this a lot with the way the the way the skull moves over its attachment with the vertebra. So when you see the resistive, it's gravity's pull on the center of mass of the head. And then the effort force, the muscle force, is the way that the spinal extensors attach to the skull in the back. So here you have your skeletal muscle force, here you have resistive force, and they're going to play back and forth in relationship to here. Second class levers are where the effort force and resistive force act on the same side of the fulcrum, as in a wheelbarrow. So if I look at this wheelbarrow, here is the axis of rotation. We have the resistance force, which is the weight within the wheelbarrow, and we have the effort force, which is the person pulling up or applying the force to lift the wheelbarrow. This has a mechanical advantage of greater than 1. So again, now we're looking at it's magnifying the effort force as opposed to the resistive force. An example of this in the body is toe raises. So if I do a toe raise, it's very important that you see where the axis of rotation is, and that is where your foot is hitting the ground. So this is the axis. You have the weight or the resistance of the body coming in between where the calf is coming around the calcaneus and pulling up. So the calf raise is an example in the body, or toe raise, of how a second class system works in the body, where the wheelbarrow is it in the real world. And the final one is the third class, and this is where effort force and resistant force on the same side of the fulcrum. Again, however, the effort arm is between the resistance and the fulcrum. So where we just had the other one, they're swapping from the second class lever. And this is where the majority of the human structure is created. So think of the bicep, where the elbow is the axis of rotation. The resistance due to gravity is out where the center of mass of the forearm is, and it added, if you have weight in the hand, it may become a little bit more. But the fulcrum, or sorry, the effort force is where the attachment side of the bicep and all those that are elbow flexors are located. And those are much closer to the axis rotation than the moment arm of the resistive force. So again, here is that creation. With the moment arm less than 1, and this is again favoring speed and range of motion. So these are not force producers, where if you look back at the last one where we're doing calf raises, those are favoring force production. So these are just a couple examples of how to remember lever systems. And the abbreviation here, F is fulcrum, force applied, A is the axis of rotation, and R is the resistive force. Okay. So these are examples of class 1, class 2, and class 3, what they are in the environment, and how they look like in the body.